splitty string thingy? This guy.
Yeah.
Okay, so now I gave you a bunch of like starter. I told you exactly how to write it, right? All right, so here's our string. So we're actually going to follow the instructions here that I wrote so you can kind of see how we're filling in the blanks. All right, so this is our string we're going to pass to this guy. So we're going to start with an empty string that we're going to end up building up. So we'll call this guy string answer. We'll start this guy off as the empty string. Then we want to go through the entire string. So that's going to be our kind of our standard for loop that starts off at 0 and goes all the way to the length of the string -1. So for int I is equal to 0, I is less than s dot length, I plus plus. All right, then we have some logic we're going to put in here. So each character is either a comma or not. If it's a comma, if it's not a comma, concatenate the string we are building. If it is a comma, print the string to the up to that point and set it to the empty again. Okay, so I'm going to drop that stuff inside of my loop. And we're going to ask that question. So if the character I'm currently looking at is not a comma, so if s dot char at I is not equal to a comma, then we're going to say answer is equal to answer concatenated with s dot char at I. Otherwise, it says print the string up to that point. So I'll print out answer and then reset it to the empty string. System.out.println answer. And then answer is the empty string. Lastly, once the loop is over, I should have one last string to print. So print it. System.out.println answer. And then my function is over because this guy does not return a value, Luke.
I see.
All right, so now we'll test this guy. Just a class method or an instance method?
Class method.
Class method. How do you know it's a class method?
Static.
Static. All right, so how do you call class methods? Using the name of the class in which the method was defined. So this guy was defined inside of a class called driver. So we're going to say driver dot print parts. The string we're going to pass it is S, and this should print out Matthew, then Mark, then Luke, then John to the screen. There's our Matthew, Mark, Luke, John. Make sense? So did you see how I literally followed the, I'm going to call it pseudocode that I gave you last class? I just told you exactly how to solve it. You just had to convert that into the equivalent Java, right? Okay, so if you followed it that way, you could get it solved. I've already looked at a couple of these, so some people solved it in kind of a strange way, but that's okay. So let me show you some alternate approaches. So since we are just printing to the screen, what some folks did is they didn't build up a string here. So instead of creating a string and building it up, what they did instead is they printed system.out.print s.char@I. So rather than build up a string and then print the entire string at the end, they just printed the string one character at a time. So, you know, M, A, T, T, so on and so forth, until they finally hit a comma. Once they hit a comma, they kicked it down a line.
There we go.
And went back to the races. So this will solve it too. Oh, what did I do? I have a variable I didn't use.
For some reason, your cat is pulled up there.
It's a comment. This shouldn't be a problem. Here's my last one. Oh, this actually would be an issue because you print out all the things. No, this would be good. You don't need it because you're actually what you'd want to do is you'd want to kick it down one more line because you were in the middle of writing your last one. So JOHN, you're still sitting at the end of that last line when the loop ends, so then you just kick it down so you're at the next line. But in any case, this guy will give you the same output. We just solved it by printing one character at a time rather than building up strings. Make some sense? Mm-hmm. All right, questions about that one? So the solution I would probably go with is that solution, the one I originally wrote there. We're building up a string. When we hit the end, we print out that string, then zero it out, and at the very end, print our final string. All right, so I will go ahead and post that on Slack. Remember, this extra credit opportunity tonight, 6 to 9 p.m. in the auditorium, the Take Back the Night. Take a picture of yourself there and email it to me, and I'll give you the extra credit token. Yeah, so that guy is tonight. Then there's this other one that's October 13th. That's like a Psalms Bible study here on campus. It's $10 registration with the Concordia Bible Institute. If you want to go to it, but the $10 is a problem, let me know, and I'll sponsor it for you. If the $10 isn't a problem, don't just steal $10 from me. But I will pay for it if that's the thing holding you back. Go ahead.
Like the extra credit, what does that work? You just get the extra credit, or like
what I do is you're going to have a collection of tokens in the grade book. So there's already a thing that's called like EC token or something like that. And then at the end of the semester, when I go to calculate your grades, I'll look at how many tokens you have, and I'll go through and look at all the homework assignments and quizzes, and anything that's not 100 will become your lowest ones will go up to 100. So if you miss a quiz, you get a 0 on that'll become 100. If you based everything, because if you got a 92 in a homework assignment, 92 becomes 100. You know that. So it'll replace mistakes or missed quizzes or that kind of stuff on homework assignments. Won't benefit you on exams, but it'll keep your homework average up, which is 60% of your grade.
I would come good in that class.
Yeah, it doesn't really change my life at all today. Just make sure you always return a value when you're supposed to return a value. No promises. Oh, I was getting ready to post some code, right? Okay. So this is split string thingy. Okay. Have we looked at arrays yet?
No.
We should probably look at arrays. All right. So let's go here.
Is it the char at gonna split out the number?
Who?
Like char at position I, is it gonna split out the number?
If there's the number at that position.
Probably like
Char at bucket 3 would spit out whatever character lives at bucket 3 in the string. If that's a digit, that's a digit. If it's a comma, question mark, the letter A, whatever.
It can't be a string, right?
It can't be a string because strings are collections of chars.
Okay.
So s.char at I will always, 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 always return a char.
Okay.
Where a char is any one of 65,536 characters. What was I doing? Oh, this. Okay, so let's talk about arrays. So arrays, and we're gonna say that these are like lists in Python. This is mostly a truth. Actually, in Python, lists are implemented as something called a linked list, which we'll talk about next semester. But from our perspective right now, an array, just like a list, is a collection of like values. So actually, let's call it like types. So you can have a whole bunch of integers in there, a whole bunch of chars. You can have a whole bunch of strings, so it can be object types as well. So a collection of like types is an array. Syntax for creating array is the type followed by opening and closing square brackets. I'm going to put a little space in there. There's not supposed to be a space. So there's no space in here really. I just put one there so you can actually see that there's square brackets. All right. Yeah, otherwise they merge together into this weird thing. All right, so you have, so I'm creating, now remember the syntax for creating any variable is the type followed by the variable name, followed by an equal sign, followed by the value, right? An array is no different. The type of what I'm creating here is an array of this type. So I'll show you an example here in a second. So then we have var name equals value. Okay, but now specifically for an array, I'm going to replace value with new type, open square bracket, size, close square bracket. So for example, if I want to create an array of integers and I want to be able to hold 10 integers, this is something that we did not have to do with lists in Python. In lists in Python, we just said, okay, this is a list. I can just add stuff to this list to my heart's content. In Java, when we create an array has an initial fixed size. All right, so for instance, if I want an array of 10 integers, I'm going to create a variable of type int array. I'm going to name this guy AR. He's going to be equal to his value. The value is going to be a new int array of size 10. That's how you would create an integer array in Java that can hold 10 things. All right, so let's talk about a couple of these pun intended new things here. All right, so we got this keyword here. We got a new keyword called new. So the new keyword we want to think about as our real estate agent. This guy's job is to talk to the operating system, or in this case, actually, it's the Java virtual machine for Java, and ask for a chunk of memory big enough to hold the number of, well, let's just say big enough to hold the values we are trying to store. We're seeing it related to an array right now, but shortly we're going to see it related to creating objects as well. All right, so I think about this as our real estate agent could, in real life, if you want to build a house and you want this to be a 3,000 square foot house, let's say, so pretty good size house. You talk to the real estate agent, you show them the blueprint so they know how much land you need, and then they go out and they find a plot of land that's for sale that will fit your house. Now, I can't give you a half-size plot of land, right? You know, because a half-size plot of land won't fit the whole house. You'll have to split the house between two, and that won't work, right? So they're going to have to go and find a chunk of land big enough to hold the house that you want to build. All right, so the new keyword is like that. You're saying, I want to build something that's this big. Go and find me a place in memory to build it. All right, now, specifically with arrays, memory must be contiguous, which means in a row. So when we request that memory, when we say, like this guy right here, we're saying, in fact, let me steal this and just I'm going to give ourselves an example here. So when I say something like int array AR is equal to a new int array, I'm just going to go 4. That way I can draw my picture and not have to draw a zillion buckets. Okay, what this is saying initially is find me enough memory that is all next to each other. So memory in a row to hold 4 integers. So we ask ourselves, how big is, and are you guys looking for Gary? Did you have were you sit? Oh, he's here, but he might be teaching. Yeah, so he might be now in that room. Otherwise, maybe after this class, he'll be available for like a half hour. So at like 11:20. So find me enough memory that is all next to each other to hold 4 integers. So how big is an integer? An integer might be, well, how big is an integer in Java? How many bits is an integer? 32 bits, or 4 bytes, right?
Okay.
4 bytes. 1 byte is 8 bits. 8 times 4 is 32. Same number. Okay. So that means that what we actually need is we need 16 bytes of memory, or 128 bits of memory to hold 4 integers. So we're asking this real estate agent, the new keyword, to go out and find us this much land that's right next to each other. So we need 16 bytes of memory that's all next to each other in the computer's memory. We don't have to worry about that. That's just what the new keyword's job is. We say how big we're going to build, and they're going to go and find us a place to build it. Okay, that's their job. All right, so once we have my memory, the new keyword is going to return for us a memory address. Now let me prove that to you here. So I'm going to create an int array AR is equal to a new int array 4. All right, so that is asking, the new keyword is going to go and talk to the Java virtual machine and say, hey, I need enough memory to hold this many of these guys. So it's, in this particular case, that means I need 16 bytes of memory next to each other. So then if I go and I print out system.out.println, I print out AR, I'm going to get weird looking memory address. All right. Because the value of AR is this goes back to how do variables work. Syntax for a variable is type var name equals value. The value in this case is this guy right here. It's the value that is returned by the new keyword when we say, give me space for 4 integers. And what it's going to do is it's going to return for me the memory address where that memory starts. So this is actually the base address. So AR will hold the base address of our array. And that'll make sense here in a second. All right, AR will hold the base address of our array. And then I'm going ahead and I'm printing out AR. And we're like, well, AR is an array. Well, no, AR points to an array. AR is a variable that holds a memory address. The new keyword always, always, always returns a memory address. Okay, and that memory address points to the place in memory where our integer array lives. Make sense? All right, so that's why I get the weird memory address here. From our perspective, we don't care what that thing is. We just should expect it to be a memory address because we saw the new keyword here. All right, so now we're going to look at how do arrays actually work. So I'm going to draw some pictures. There's this guy. Okay. So we're going to say there's the values of my array. This is bucket 0, bucket 1, bucket 2, bucket 3. Down here, I have my variable named AR. And AR is going to, actually, let's do this. AR is going to hold a value. Now, just for the argument here, we're going to make our value an easy looking memory address. So we're just going to say it's memory address 100. Okay, instead of weird looking crazy hexadecimal value. This is still a legal hexadecimal value. It's just a simpler one for us to deal with, right? All right, so AR actually holds the value 100, and this guy is the base address. Where our array lives. That's what that 100 is. So what I'm going to do is I'm going to put 100 here. 104. 108. 112. All right. I'm going to draw a little arrow. This is where my arrows are. All right, so AR holds a memory address which points to the base address or the very beginning of where my array lives in memory. Now, the way we access individual buckets of my array, so for instance, if I want to put the value 5 here at bucket 2, I would say something like AR at bucket 2 is equal to a 5. But now we want to know, well, what does that ultimately mean? This guy translates into go to the base address AR, add to it 5 times the size of, in this case, int, and set that equal to a 5. Well, what's the base address AR? That's 100. What's the size of an integer?
32.
4 bytes?
Or yeah, 4 bytes.
Yep, which is 32 bits.
Yeah.
5 times 4 is
20.
20. What's 100 plus 20?
120.
Actually, hold on. I wrote this poorly. This is not 5. This is... I'm putting a 5 at that bucket. We're going to bucket 2. AR at bucket 2 is where I'm going. I'm putting a 5 there. So it says go to the base address 100, add to it 2 times the size of an int. So 2 times 4 is 8. 100 plus 8 is 108. And that happens to be where bucket 2 lives. All right, so I'm going to write this again, just since I confused you at first. So this is going to be AR plus bucket num times size of type. So in this case, we have an array that is type int. Our base address for AR is 100. We're going to add to that whatever bucket number we're looking at, which is 2 in this case, multiplied by the size of the type we're storing, and we're storing integers. It's an int array. Size of an integer is 4 bytes. So 2 times 4 is 8. 100 plus 8 is 108. So AR at bucket 2 says go to memory address 108 and put that value there. So that'll put the 5 right there. Go ahead.
Can you just explain again what, I don't understand what 100 what those are.
This new keyword is going to return a, shut up! This new keyword is going to return a memory address like this guy. So instead of a weird memory address like that, I just assumed it returned a 100 because it was an easier value for us to work with. Okay, so when we created our array up here, we said int array AR is equal to a new int array capable of holding 4 elements, 4 integers. So the real estate agent went out and found us some memory that can hold 4 integers in a row. It returned for us that memory address. When I printed out AR, it printed out that memory address. So back in here, I assumed that this new keyword here returned for us the memory address 100, just to make our math easy for us to see how it works. So that 100 is what's returned by the new keyword when we create this particular array. So now if we want to start putting stuff in our array, so let me show you the actual code up here. I can say AR at bucket 2 is equal to the value 5. Then if I say system.out.println AR at bucket 2, this will show me the 5 I have stored at position 2 in my array AR. So there's my 5. So now what I'm explaining is, how does this syntax work? This syntax says I'm going to store a 5 in this array at position 2 in the array. I often call it bucket 2. So how do we get to that? We go to wherever AR starts, and then, because that's the base address of our array, and then we take 2 integer-sized steps from that base address. So we come back here. How big's an integer? It's 4 bytes. So I started at base address 100. I took 1 integer-sized step that took me to 104. I took another integer-sized step that took me to 108. How did we calculate that? We said start at base address AR, add to it the bucket number, or we can think of it as the number of steps we want to take from the base address, multiplied by however large the size of value we are working with is. So in this case, we're working with integers, so that's 4 bytes. We're going to bucket 2. 2 times 4 is 8. Add to the base address, which is 100, so 100 plus 8 is 108. So the place we're ultimately storing, humans like saying AR at bucket 2, but the computer is going to map that to say I'm actually putting this value at memory address 108, which is big enough to hold an integer. So I'm putting that 5 there. So as a Java programmer, you will never write this. You'll always write your code like this. That's more human friendly. AR bucket 2 equals this value. But now if you were in a C or a C++ programmer, you could choose to walk arrays in memory. You could choose, instead of using this friendly syntax, let's say, you can choose to have direct access to memory like this and say, I'm going to go to this memory address, I'm going to add to that these values, because you can do what's called pointer math in C and C++. Why can't you do that in Java? Glenn?
Because it's like the whole virtual machine thing, so you're not actually using, like, it's creating software in hardware, so like it's not actually, like, you can't directly interpret with the memory since it's like separate, I guess.
Well, we'll start off with this. Well, let's write a thing called pointers. What's a pointer? So a pointer is a variable type capable of holding a memory address. That's what that is. Okay. An int can hold a whole sign number. A char can hold a whole unsigned number. A boolean can hold trues and falses. A pointer can hold memory addresses. Okay. The second we start thinking about memory addresses, things get very scary for programmers. Okay, it's an intimidating type thing. But if we think about them as values just like any other value, which is a street address, we're not intimidated when somebody says, oh, go to the McDonald's on Port, here's the address. You know, and a human address is very crazy looking, right? You know, we have a number, a house number. Then we have a street name. Then we have a city, a state, a zip code. We have a whole bunch of pieces of information that relate us to where a place is in our three-dimensional world, Earth, right?
Mhm.
Okay, so we can go to, it could take us to any country, all sorts of stuff like that. In computers, memory is far simpler, even though it looks more intimidating because we're not used to using this. In computers, everything's on one street. We have this big, long street here, and we're saying that the value we want to go to is house number 108. I'm starting here, and I'm just going to zip down the street till I get to house number 108. That's the address. Now, we look at something like this, and we say, well, that's not a 108. Okay, that's a crazy-looking hexadecimal number. Well, all a hexadecimal number is a base 16 number. If we converted it to base 10, which is our numbering system, it would still be a scary number, but it would have less weird stuff in it, right? It would just be an even bigger number, footprint-wise. So why do you think computers use hexadecimal to represent memory addresses? Go ahead.
Because we need a lot of them.
Okay, we need a lot of them because our memory's big. So how many integers fit in your computer's memory? Let's say our computer has 8 gigabytes of memory. All right, and we'll just, for this example, we'll assume that nothing else is taking up any of our computer's memory. Operating system, all that stuff is just, it weighs 0, no calories. Okay, so we have the full 8 gigabytes of our RAM. How many integers fit in 8 gigabytes of RAM? Well, how big is an integer?
4 bytes.
Okay, integer is 4 bytes. How many bytes is 8 gigabytes? Start with that, right? So 8 gigabytes is, so that's 8 times 1024 gets us to megabytes, times 1024 gets us to kilobytes, times 1024 gets us to bytes. So let me copy that.
There you go.
Didn't we see that we can put that in here and it gives us a number?
168 million.
Gigabytes, megabytes, kilobytes, bytes.
Why is it 8? Just 8 gigabytes. Oh. Yeah.
All right, so this is the total number. Okay, now why? Best Buy used to do this kind of stuff. So instead of going and buying an 8 gigabyte chip, instead you would buy, let's make sure we read the number right. Okay, we like, oh, well, right over here we have an 8,589,934,592 byte memory stick for you. Or if you want to say that shorter, it's an 8 gigabyte memory stick. Those are the same number. Make sense? All right. So this is the total number of bytes you have if you are working with 8 gigabytes of RAM. Now, each of my integers is 4 bytes.
Mhm.
So I need to divide that guy by 4.
Yeah.
Just steal the math again.
You need to put it in pre.
Nope. Multiplication, division, they'll go left to right. They're equal for, huh? Yeah, so addition and subtraction are the same weight. So multiplication or division will always happen before addition and subtraction. But then if they're the same, if you have addition followed by subtraction, it'll just go left to right. But if you want to put it in parentheses, you can do that if that makes you feel better. It's not going to be wrong. All right. So that means we can hold
There's about 2 million.
2.1 billion integers. Make sense? Go ahead.
I think you were kind of explaining it, but when you're dividing by 4, after you multiply all these together,
Yeah, this is the size of an integer. Size of an integer is 32 bits or 4 bytes.
after you multiply all the first numbers.
Well, yeah, because what I'm doing here is I'm taking 8 gigabytes. I'm saying, okay, well, 8 gigabytes is how many bytes? So 8 gigabytes is this many bytes. Then I'm dividing that by 4 because I want to know how many integers will fit in that many bytes. And it's this many. All right, we're going to put parentheses in there. There we go. Okay. And actually, if you want to put these on separate lines so we don't confuse the, so that's that conversion. Then we're going to take the number of bytes divide it by 4, which is the size of an int. And that then gives us this 2.1 ints. So 2.1 billion integers will fit into 8 gigabytes of RAM. Okay? So if we want to think about a street where each house is 4 bytes big, it's one of those subdivisions where every house is the same. Okay, so every house on this whole street is 4 bytes big. We have 2.1 billion of them. So if I want to go to my first integer, let's say in our array, I'm going to run to house number 100. Okay, the next guy his yard ends at 103. The next guy's yard begins at 104. Next guy's yard begins at 108. Next guy's begins at 112. Make sense? Mm-hmm. That's how we're walking through memory. That's how memory works. And in computers, memory is far easier than our real life memory addresses or real life, street addresses. But the second you make something look hexadecimal, we get scared, right? Because it just feels intimidating. All right, so that's one of the reasons why I like conversion questions. We had them in 200. You'll have them in here. You'll have them in every class you ever have with me. You'll have conversion questions. There'll always be at least one on the exam. Even if it has nothing to directly do with the topic of that class, there'll be a conversion question. 100%. It should be free points. Go ahead.
Can you look back at the memory address real quick?
Yeah, the real one?
Yeah, the real one.
This guy?
Yeah. So what's the?
Yeah, here.
The last digits make sense. But
Yeah. Let me. I'll paste it in here so we can see it since it's tiny text there. Yeah, so an example of a memory address we get from Java is something like this. So I mentioned that Java runs in a virtual machine, right? So it actually is giving you Java creates kind of fake memory that lives on top of your real memory.
Okay.
So this is saying this is the actual memory address. This is the Java virtual machine based memory address. And the way Java internally maps their memory, they're saying this is an integer array that lives at that address.
Okay.
So the little square bracket says it's an array. The I says it's an integer array. The at says this is where it lives. Here's the actual address. So if we want to operate off of that, we say, okay, well, we have the hexadecimal value that was weird. 277C0F21. Okay, so that's our actual address that Java gave us. If we want to convert that guy to decimal, what do we need to do? Well, so this 1 is in the 16 to the zeros place. The 2 is in the 16 to the 1's place. The F is in the 16 to the 2's place. So I'm going to kind of write it out that way so you can see what I'm talking about here. If we were dealing with a binary number, this is the 1's place, the 2's place, the 4's place, the 8's place, the 16's place. If it was a base 10 number, this is the 1's place, the 10's place, the 100's place. This is a base 16 number. This is the ones place, the 16s place, the 256 place, the 4096 place, the 16,536 place. Yeah, I'm probably gonna. Then it's 2.1 billion place. 16 to the 4. Okay, so that's my 4's place. So then the 5's place is 1 million's place. All right, so to plan this out, this is 1 times 16 to the 0's place. Then it's 2 times 16 to the 1's place. Then it's F times 16 to the 2's place. Then it's 0 times 16 to the 3's place. Then it's C times 16 to the 4's place. 7 times 16 to the 5's place. 7 times 16 to the 6th place, and then 2 times 16 to the 7's place. All right, so we said that this is 1, the 1's place. I do it like this. This is the 1's place. This is the 16's place. This is the 256 place. This is the 4096 place. This is the 65,536 place. Times 16 is this number. To the 6th place is this number. To the 7th power is that number. So 1 times 1 is 1. 2 times 16 is 32. F times 256. F is the number 15. Hexadecimal values are 0 to 9, then A through F. So an F is a 15. So this is 15 times 256. Which is 3840. And then this one's easy, 0. Got a freebie. 0 times whatever this is going to be 0. Okay, then C, so A is 10, B is 11, C is 12. So this is 12 times 65,536. And that's this number. And then 7 times this number is this number. And then 7 times this number is this number. And then 2 times this number. I don't know why it didn't auto finish that for me, but whatever. Is that number. So now we add all these up. So we're going to have this number plus this number plus this number plus this number technically plus a 0. We'll throw it in there for completeness. Plus 3840. Plus 32. Plus 1. Which is that number. $662,441,761. So this guy right there is this number right here. This is hex or base 16. This is decimal or base 10. Go ahead.
Is there like a number different for capital A or like the regular A?
No, it depends on which reference you're looking at for hexadecimal. Upper and lowercase a are the same. They're both 10. Historically, I typically will see it written with uppercase letters, which makes it kind of funny where, as I've seen it, most programming languages, when it prints out the memory address, is lowercase letters, but they're interchangeable. Yeah, so base 16 is 0 through 9, A through F. Base 36 is 0 through 9, A through Z. Make sense? After that, you got to, I think, last semester we talked about like tacking on Klingon and stuff like that. Yeah. Yeah, Klingon actually has a smaller character set than the English alphabet, so we actually hurt ourselves that way. I think there's only 22 characters in Klingon.
Well, if we add it on to
What's Klingon? Have you considered changing majors?
I used to.
Have you heard of Star Trek? Never heard of the show Star Trek? Have you considered changing majors? Star Trek's kind of a famous-y old sci-fi show, and they've made a whole bunch of more recent movies based on it. Spock? You've heard of Spock?
There's a Klingon berry.
Huh?
There's a Klingon berry.
A Klingon berry? Okay. Yeah, you see this thing? This is Spock. Live long and prosper. Killing me. Yeah. Some point, look up Star Trek. Why? But in any case, in Star Trek, there's an alien race called the Klingons, and this is a made-up alien race.
No, it's real.
It's real. So this is a made-up show, a fictional show with a fictional alien race in the show that has a fictional language called Klingon that somebody has actually created the language for.
So it's actually real language.
So a bunch of nerds have made the Klingon language. And at the end of the day, for us, what's important is that it's a less efficient language to use for representing various bases because there's less characters in the set. Okay, so for us, the best we can do is up through base 36. After that, you're going to have to agree with the other person you're working with numbers for what comes after that, because every character needs to be a single slot. Mm-hmm. So you could always use the Unicode character set where you get into all the kanji characters and stuff like that from all sorts of different languages. So technically, you could have 65,527. So you could have up to base 65,536.
Or you can use Swift and use emojis.
Well, you can always add emojis in there. It's true.
Don't make things more complicated.
But in the world of computers, we typically operate in 3 bases. Well, yeah, really 3 bases: binary, octal, which is base 8, and hexadecimal, which is base 16.
Okay.
Then you throw humans into the mix, and we throw base 10 in there. Make sense? Okay. So when you in the computer organization class, we kind of talk about the meaning of why you have all these different ones. For us in here, we care more about the pattern of converting. We wrote a program for it last semester.
Mhm.
We're going to do it again this semester to remind us. Right? All right. So super easy math right here. The math was easy. It was just tedious, right?
Mhm.
So of course, on an exam, I would give you something that's at least this difficult, or at least this tedious. I would give you something significantly shorter than this on a quiz or an exam, but you'd still do the exact same process. I mean, the process isn't going to be any different. You might just have to go down to this level or something like that instead of all the way down to this many places. All right. So this memory address translates into go to memory bucket level, or memory bucket 662,441,761. Go to that house down the street.
Family knows that's doing just that.
All right, we'll go back and rewatch the video. Because it's kind of a long, drawn-out thing. So if the end result didn't make sense, I think you're going to just have to listen to the cadence again. All right, because that's how memory in our computers work, right? One big, long street, as opposed to having houses and cities and different streets and all this other stuff. So memory in computers is easier. We think of it as just this house number. Computers represent it as hexadecimal for various reasons, one of which we might say is that this guy typically gives us a smaller footprint. So this is what, 3, 4, 5, 6, 7, 8, where this one is 9 characters. We saved ourselves 1 character in this case. But typically, hexadecimal will give us will give us a smaller physical footprint for the size of the number. But there's some other advantages to hexadecimal that we talk about in 325. So it's not a topic for this class. All right. So when we see a crazy looking memory address like this, know that it actually is equal to some decimal number behind the scenes if you really cared what that number is. And it just tells you how many steps into memory do you need to go to get to where this value starts. All right. But as programmers today, we don't even care what this number is. We should know what this number is. We should know what it represents because we want to understand the theory of computer science, what happens under the hood. But as a practical programmer today, you can get by with just saying, I want to go to AR at bucket 2. Because what this is ultimately saying is go to memory address 662,441,761, then take 2 integer-sized steps from there and stick this value in that bucket. Build that house there. That's what that ultimately means. But as a programmer today, we don't care what AR actually equals. We just say, Java, take me to the beginning of my array, wherever that is, and then give me an offset of 2 integers from there and put this value. But if we were a C or a C++ programmer, we actually might care about that those memory addresses because there's this thing called pointer math that people would do stuff with pointers. And I asked a question a little bit ago, and I'll come back to you, but I asked a question a little bit ago about why We have pointers. So a pointer is a variable type capable of holding memory addresses. Well, as far as we know, the variable types that exist in Java are byte short, int long, float double, char, boolean.
Mhm.
Those are our primitive types, and then we have that catch-all object type that we can make all sorts of objects and stuff out of it. In Java, we don't have. Most textbooks will say that in Java. Oh, and remind me at the end of class today, I want to give you a reading assignment that'll catch you up to arrays in our book, and I think that'll help flesh out the other side of this coin. But in any case, a lot of Java textbooks will mention that pointers do not exist in Java. They'll say something along those lines. Pointers do not exist in Java. Okay, and all we have to do is write this little tiny program like this, where we see a memory address, and we can say, AR, I printed out AR right here, right? And what printed out here? A memory address. What's a pointer? It's a variable type capable of holding a memory address. Do I have a variable here that is holding a memory address?
Yes.
Yes. Memory addresses, pointers exist in Java. What we don't have in Java, we do not have a special syntax for working with memory addresses in Java. All right, in a language like C, let me just show you this. Let me go online. C compiler. I usually do this on my Mac, so it's I don't have to worry about this. But I can find an online one here real quick and write you some C code to connect some dots here to our older C-based language. This seems way worse than 5 seconds, doesn't it? Perfect. All right, so can I make this bigger over here? All right, so we can see that? All right, so what I'm going to do is I'm going to do the equivalent of our 4-bucket integer array in C. But I'm going to do a couple of different ways here. See, it's standard lib, I think. Don't worry about that. So I can say int AR4, and then I can say AR at bucket 2 is equal to 5, and then I can say print F %D AR at bucket 2, something like that. And there's my 5. So I created an integer array. So syntax is a little bit different, but most of this looks similar, right, to what we're doing? Mm-hmm. Okay, so this is C. So I created an integer array capable of holding 4 integers. Then I said I'm going to set bucket 2 of that guy equal to 5, and I'm going to print out the 5. Okay, now that's not the way the cool kids would write it. Cool kids would write it this way. I'm going to say I'm going to create an int pointer. So I mentioned Java does not have a special syntax for representing pointers. C and C++ do. So I'm going to create a variable of type int pointer, so a little asterisk there. I'm going to call this guy AR2, and this guy is going to be equal to malloc. So I'm going to allocate some memory. That's what the new keyword does. So malloc and new are the same. They're first cousins. Okay, something like that. All right. Malloc's job is to allocate some memory. How much memory? Well, I want 4 times size of an int. That's how much memory I want you to go give me. So this guy here and this guy here are going to do the same thing. Technically, this actually lives in OS space, where this lives in user space because of the way we created it, but don't worry about that for right now. They both ultimately do the same thing. They give us enough memory to hold 4 of these guys. But in this case, I'm asking the operating system to allocate for me 4 times the size of int in bytes. Give me that many bytes. So this will ultimately allocate 16 bytes of memory. All right. Then I'm going to go ahead and say I want to store AR2 that's the base address plus, and we're doing bucket 2 here. Trust me when I say 2 here is the same thing as saying 2 times size of int. It knows that I'm talking about an integer array. So when I add 2, it says take 2 integer size steps. So I'm saying AR2 at position 2, the value at that is going to equal a 5. And then I can go ahead and print it out. Print out %d, that's a placeholder for a decimal number. And I can say the value that lives at AR2 plus 2. Now I'm going to show you a second line here. If instead of the value that lives there, I wanted to instead print out the memory address, I say I'm going to print out, this is a placeholder for a pointer. I'm going to print out that memory address. Oh, whoa. Am I completely dead? Can I hit back and will that be a bad thing? Ah, there we're good. What don't you like? Oh, I need the asterisk there, don't I? Yeah. I want to set that value AR2 should just have the memory address. Does it want me to say the value at that? I'm only going to mess with this for a second because that's, I don't want to go too far into this. This says base address AR2 right here, plus 2, set that equal to 5. But I want to set the value at that place equal to 5, so that's correct, the way I have that written. Size event there, this closes there. Just make sure my malloc is working correctly. Yeah, so that's working correctly. If I print out the value that lives at bucket 2. Oh, it's not letting me walk memory? Okay. That's the default value that lives there, which means that it wants me to do this. Put at the address of that guy? Why are you upset with this? That should be good syntax. Oh, well, whatever. I'm probably just doing something stupid here. But in any case, I'm creating a array of this size by allocating some memory, which is the same thing as the new keyword. I'm using pointer math here, saying go to this base address, take 2 steps, put this value at that position. And it should have an asterisk there. That's the value at that position. And then I'm printing out the value here. But in any case, this is showing us where it came from. Punchline for us in here is C and C++ have this special syntax for dealing with pointers, where Java does not have that syntax. We lose control over doing pointer math inside of Java. All right. For next class, I'm going to give you a reading assignment for the book and go through the exercises. This should hopefully help get you up to date with the other things. I'm going to have you this side. All right. Read 5.1 through 5.8. So this is dealing with single dimension arrays. Do the exercises. Expect a quiz over arrays based on what you're reading there on Thursday. All right. So no programming assignment though. We didn't get far enough into arrays, but there will be an assignment that I'll give you on Thursday. All right. So 5.1 through 5.8. Everything up to but not including 2-dimensional arrays. All right.
You want us to submit anything in Blackboard for this?
No,
What?
just read it. Be prepared for a quiz.
Oh.
Nothing to submit.
That's easy enough. Literally,
Got it today.
Or don't read it and come and bomb the quiz. Remember today, student, faculty, staff Bible study. God and grub. Go down to the cafeteria, grab a tray, sign in. Take your tray down to the terrace room. Computer science has a table. You're welcome to sit with us, but you don't have to.